Welcome to EPG Pathshala lectures on numerical methods. This is second module on direct methods for solving systems of linear equations. The model objective set here are the basic Gauss elimination algorithm. We have already seen basic Gauss elimination method. Now, we are going to talk about computer implementation of that. Gauss elimination with partial pivoting, that is what we will try to understand. Gauss-Jordan method we will consider, and computational aspects of these methods we will try to understand. In the last module, we have already seen the general systems of linear equations, methods, what are the methods available for finding solutions of such systems of equations, and we have seen the basic Gauss elimination method was already discussed. In this module, computer implementation of the Gauss elimination algorithm, that is this method, we will see the what changes we will have to make in the computer implementation of that, and its limitations will be discussed. The modified Gauss elimination with partial pivoting will do, and the Gauss-Jordan method and their computer implementation will also be discussed. So, this is what we will be doing. So, let us recall in the Gauss elimination method discussed in the previous module, separate variable names used for storing the modified matrices at kth step. You know that Gauss elimination method was in n minus 1 step. In each step we modify the coefficient matrix A. So, after the kth step, whatever matrix augmented matrix we get, A k B k is the notation that we use. So, in the sense of computer implementation, all these variables will be occupying separate storage space. So, this is good for understanding the method, but not desirable for computer implementation, as it uses lot of memory space, because new variable name will require new space to store the intermediate matrices, which are not at all used in the final computation. In the final computation, we are using only a n minus 1 and b n minus 1. We are not using all intermediate matrices, and therefore, for computer implementation this may not be really good. So, we use the same memory locations to store the original matrix and all its subsequent modifications. So, when you are taking original matrix, you will be storing it in A, B, 2 dimensional array A and 1 dimensional array B, and then we will be doing this augmented matrix A B we will be doing, which can be considered as 2 dimensional array straight away, and therefore, the computer algorithm must slightly differ from the procedure described in the previous module. So, we will be slightly changing that procedure, which is essentially the same, only thing we are trying to save our efforts on computations. So, changes in the manual procedure required for computer implementation here we are talking about. So, observe that in the kth step we first make the kth element in each of the rows from k plus 1 to n 0. You know that we are making k plus 1 to 0. So, first column elements we are trying to make a kth element in each of the row k plus 1 to n 0. If we do the same thing in the computer implementation, then the elements computed in the k minus 1 step in the kth column of the rows k plus 1 to n will not be available for computing subsequent elements. So, if I make one element 0, then that will not be available for subsequent computation, whereas you need to use that element in computation of remaining elements of that row, and therefore, we do not make it 0 in this. So, what we do here is, so element in these rows, and hence we leave the kth column element unchanged in the kth computational step. This does not affect the further computation, as these elements are not going to be used in the subsequent steps of the elimination process. So, matrix will store those elements, below diagonal elements, in the kth step without changing them and not making them 0, because that is not going to affect my further computations. So, what we are now going to do is this. Let us look at this basic Gauss elimination algorithm. So, what modifications we are suggesting, we are going to write them over here. So, I am taking now input to the system as size of the system n, coefficient matrix A, Aij equal to 1 to 3 up to n and j equal to 1 to 3 up to n. We must ensure that this matrix is non-singular. Right hand side vector Bi, I equal to 1 to 3 up to n, any non-zero vector we are considering, and tolerance for the size of an element APS, typically epsilon can be taken as 10 raised to minus 5, because tolerance for the size of an element we are considering here. So, we will see how this makes changes into the process here. Output solution vector xi I equal to 1 to 3 up to n. Now, we are going to talk about this. So, we are saying that elimination process starts with row k equal to 1 to up to n minus k, the step k equal to 1 to n minus 1. So, there are n minus 1 steps. So, k represents step 1, step 2 up to step n minus 1. Now, if I am saying if a k k, that is a diagonal element, because we are dividing it by a k k in every step actually. So, that diagonal element should not be 0. If it is 0, then division by 0 may occur, and that is what we want to ensure, or that is what we want to take care in the computer algorithm. So, if a k k is less than epsilon, this is what where I am using this epsilon. So, size is alarmingly small, then we say that print division by 0 may occur and terminate the algorithm. So, we will not proceed further at all. So, if at any stage of the elimination process the diagonal element becomes alarmingly small, then we will terminate the algorithm. After ensuring that this is not so, we will go to the further computation in the kth step, and for I equal to k plus 1 to n. So, now we are considering k plus 1th row to nth row, that is what we are calculating, and then we are doing j equal to k plus 1 to n. In the manual procedure we take j equal to k to n, because the kth column element will become 0 in that sense, but here we do not want to change that kth column element, and therefore, we are taking modification from k plus 1 to n, and then you are using just implementing the same formulae as we have stated in the manual stated in the basic Gauss elimination algorithm. So, Aij, any cell Aij element we are considering is equal to Aij minus Aik, that is Aik star. So, this is element in the ith row in the k column multiplied by Akj. So, in the jth column that we are considering here Akj. So, that element here and divided by Akk. So, we are considering this in order to modify my Aij element in the remaining rows. So, k plus 1 to n rows, and in that k plus 1 to n column elements we are considering, and Bi equal to Bi minus Aik star Bk divided by Akk. So, that is your last column of the augmented matrix, and therefore, the right hand side vector is modified according to this. So, once we do this, the process of back substitution will start. Now, when you are considering back substitution, the first thing that we are doing is that we are trying to find out x n equal to b n upon a n n. When you have reached to this stage, it means that I have not encountered any 0 element in the diagonal position up to nth step, n minus 1 step actually, and if now mod a n n in the last step mod a n n becomes very small, then I will not be able to get this, and therefore, I am saying print matrix may be singular, because it is possible that this will happen only if the matrix is singular, and therefore, we are saying that print matrix may be singular and terminate the algorithm. So, at this stage also we are taking care that division by 0 does not occur, and therefore, x n equal to this, and then the back substitution, your usual back substitution process for I equal to n minus 1 to 1 steps of this, and then we go on writing x I equal to x I divided by a I. We have already ensured that all other elements are not 0, and therefore, this will give me the values of the unknown variables. So, back substitution process ends here, and that is what the algorithm is about. So, only change that we are doing from the manual procedure is that instead of writing those kth column element as 0, I am doing processing only in the k plus 1 to nth column in the rows k plus 1 to n, and each time I make division by diagonal element, I make sure that that element is not alarmingly small. Okay. So, now we are going to consider here the same example that we have discussed in the previous module. So, we have discussed this example in the previous module. So, we solve this system using this algorithm now. So, when I am using this algorithm, I am considering here as a result of implementation of the matrix augmented matrix you take and obtained at the end of the step 3 of the elimination process, I will be getting this matrix. You can see that this below diagonal elements here, they are non-zero. So, this is they are non-zero, these are non-zero, this is non-zero, and you can see that rest of the elements will be same as the ones which we computed earlier. So, these are k minus, when you are working on kth step, these elements are from the k minus 1 step. So, k minus 1 step, like that we are saying. So, below diagonal elements anyway we are not going to use them. So, this is what I will get, and observe that this matrix is different from that obtained in the manual implementation and changes only in the elements below main diagonal, which do not affect my back substitution process and yields the same solution. So, this is just the changes in this. Now, example 2, let us look at this example now. Solve the system of linear equations represented by augmented matrix. This I am considering. This matrix was considered in example 3 of module 11, and you can see that at the end of the elimination process, the algorithm 12.1, the matrix A is reduced to this. So, when I try to do the elimination process, the matrix A will be reduced to 7 minus 7 0 0. So, now I will get here this element 0. When I get this element 0, I am going to exit my algorithm at the time of starting of back substitution process. So, this can be verified from the computations in module 11. Now, since A33 is 0, the algorithm terminates with a message that matrix may be singular, because you are exiting the process at the starting of the back substitution procedure. Whereas, in this particular example 3, if you take this and again implement the algorithm, we will see that using basic Gauss elimination algorithm, at the end of the execution of the outer loop for k equal to 1, I get this element as 0. Again, so diagonal element has become 0 in between elimination process itself, and therefore, the algorithm will terminate saying that division by 0 may occur. I am not sure that matrix is non-zero, singular, matrix is singular or what. I am just saying that division by 0 may occur, and therefore, the this will be algorithm will be terminated here. In the elimination process at any kth step, so we are now trying to compute the time complexity of the algorithm 12.1. Then we will talk about the limitations of algorithm 12.1, but before that I will just look at the time complexity. So, in the elimination process at any kth step, n minus k into n minus k plus 1 elements are updated, and each element needs 1 addition and subtraction and 2 multiplication and division operations. So, in the back substitution process, for computing value of ith variable, n minus I additions and n minus I plus 1 multiplication oblique division operations are required. See, you can look at this, all this can be verified from the algorithm itself. So, this is a back substitution process, but this is elimination process. So, we are doing what? This is executed n minus 1 times. this is executed k minus n minus k minus 1 times actually, and we are trying to find out this number of elements here. So, how many operations are required? We can see here that in this we are evaluating this step by step. So, in everywhere we are getting one subtraction, one division and one multiplication, one division operation, and here again I will have to do the same thing for this. So, therefore, I am saying here in the elimination process, at the kth step, n minus k into n minus k plus 1 elements are updated, and in each element needs one addition or subtraction operation and two multiplication and division operation. So, if you look at that loop, you can always get this statements verified. And similarly, in the back substitution process, for computing values of ith variable, I need n minus I additions, because you will have to do those additions there, and n minus I plus 1 multiplication oblique division operations are required. So, for overall computation, comparisons are required, where you are testing whether diagonal element is less than epsilon or not, and let times required for one addition subtraction as usual will denote it by one addition and subtraction, one multiplication and division, and one comparison are denoted by A, M and C, and then the maximum time required for execution of the algorithm 12.1 will be given by all this. We are putting it in the nutshell here. So, A plus 2m additions and these many elements, and you have to, this is kth step. So, and steps are 1 to n minus 1. So, therefore, these many additions for elimination process. This is for back substitution, A plus m into n minus I plus m, I equal to 1 to 3 up to n, because n elements we are computing by back substitution, and here n into C number of comparisons. So, that is what we will be getting, and on simplification I will be getting it like this. So, this will be n cube, n square, n term, and therefore, the maximum power of the n is cube, and therefore, the asymptotic time complexity of the algorithm 12.1 is order n cube. You can see that this is quite a big complexity, time complexity. So, limitations of algorithm 12.1 are what? Observe that the coefficient matrix A in example 3 is non-singular, and x is equal to 0, 5 by 7 and 1 is the unique solution of the system. See, which was the example 3? You can look at that. This was the example 3. So, if I look at this example, you can verify that in this example this matrix is non-singular, but on execution what we get is division by 0 may occur there, and therefore, what we are getting here is a problematic case. So, here we are getting this 0, and that is why the algorithm has failed, but the system has a solution, and the algorithm is not able to determine the solution, and that is the defect of this, that is the deficiency of limitations of this algorithm. So, limitations of this algorithm you can see. However, our algorithm fails to find a solution. It is possible to avoid such a premature termination of the algorithm by modifying the algorithm using the technique of pivoting. So, what we are doing is we are trying to avoid getting zeros in that locations, and we will do additional elementary row operations and bring a non-zero element in that position by interchanging rows from below the current row. So, what we are doing is this. So, in the basic Gauss elimination algorithm, in the kth step of elimination process, the element AKK plays a pivotal role, as in evaluation of all the elements in the k plus 1 to n columns, in the k plus 1 to n rows, division by this element occurs, and therefore, this is very vital element, and that we are calling it as pivotal element. Hence, the AKK at kth step is called as a pivot or pivotal element, and for successful implementation of the elimination process, it is essential that AKK should not be equal to 0. Pivoting techniques aims at bringing an appropriate element to a pivotal position by interchanging rows and or oblique columns of the current augmented matrix. So, this is what we are trying to do. we are trying to bring a non-zero element in this location. So, in order to ensure that appropriate element is placed in the pivotal position at the beginning of the execution of the outer loop in the elimination process, we find r greater than or equal to k. So, we are trying to look at rows below kth row. Okay. So, therefore, I am taking r greater than or equal to k such that mod a r k is maximum of all a I k less than or equal to I less than or equal to n. So, we are taking between k and n. So, this should be maximum we are trying to consider. So, non-singularity of A, this is Gauss elimination with partial pivoting we are talking about. So, we are trying to consider kth step, we have got a k k element here. Now, in that column we are trying to find out which is the maximum magnitude element, okay, and that element I am denoting it by r k. If a r k is not equal to 0, if this is 0, then there is nothing, I mean then what will happen actually? Then in that case we will say that the matrix is going to be singular matrix, and therefore, the algorithm will be anyway terminated. So, if this is non-zero, then if r is greater than k and if r is greater than k, that means r is not k, then we interchange kth and rth row. So, that the rth element in that column will become kth column element akk, and therefore, which will be non-zero. So, what we will do is this. So, then interchanging rth and kth row and continuing with the elimination process with this modification, the method is called the Gauss elimination method with partial pivoting. Such a selection of pivotal element not only avoids division by 0, but also reduce the round of errors in the numerical computation. Why? Because we are taking the maximum value, we are not just simply taking non-zero value, we are taking the maximum value in that column, and that we are interchanging, and therefore, round of errors also will be reduced because of that. If I want to do complete pivoting, what we will be doing is, if the pivotal element is selected from among the a I j, I greater than or equal to k and j also greater than or equal to k. That means, from the entire remaining submatrix from k plus 1 to n and k plus k to n and k to n like that, and if I try to get the maximum element in all this and then do the column interchanges and row interchanges also and bring the maximum element here, that is called as complete pivoting. So, when you are doing this complete pivoting, we will have to perform row interchanges and column interchanges. So, row as well as column interchanges, the method is called the Gauss elimination method with complete pivoting. The column interchanges changes the order of the components of the solution vector. Why? Because when you are interchanging the column, your variables are also interchanged. That means, x 1 will be changing. If I interchange column 1 and 2, then x 1 will become x 2 and x 2 will become x 1. So, therefore, we will have to keep track of this. So, what we need to do is the solution vector, and so to get the solution of the given system in the original form, we need to keep track of all the column interchanges, and which will incur lot of computational efforts. So, thus the method requires more numerical efforts, which may not be worth the benefits that we get in terms of the reduction of the rounding of errors, and that we are likely to get in most of the cases. So, you will not be able to make any more reduction of the rounding of error by doing complete pivoting. So, normally most of the methods, I mean we use partial pivoting. In most of the illustrations we will be using partial pivoting only. So, we will get here algorithm 12.2, the Gauss elimination with partial pivoting. So, this is just modification of the algorithm. So, the input output are same as that in the algorithm 12.1, because we are not changing that. The iterative step consisting of two parts, one elimination process and the other back substitution process, as in algorithm 12.1. So, there are changes in the elimination process, but the back substitution is the same as in the algorithm 12.1. So, no change in that. We just give the details of the elimination process for the algorithm 12.2. Rest of the steps are same as that in the algorithm 12.1. So, what changes we are making, that we are writing down here. So, elimination process. So, what is my elimination process? So, for step k equal to 1 to n minus 1, selecting, first we select the pivotal element. So, for selecting pivotal element, we will take maximum equal to a k k, max I equal to k, and then I am saying for I equal to k plus 1 to n, if mod a k k is greater than maximum, I will change my maximum to a I k and max I to I, and that is what we are trying to do here. So, we are trying to find out not only the maximum element, but in which row it occurs, that is what we are trying to find out. And then what will happen, once we do complete this, I will get your maximum element. So, I know what is the pivotal element that I have to use. Now, if this maximum element a max I k is less than epsilon, then I will be printing print matrix may be singular and terminate the algorithm. So, that also care we have to take in the computer algorithm. Otherwise, what we are doing is interchange max ith and the kth row. So, max ith and kth row will be interchanging. So, j equal to 1 to n temporary. So, you put it in the temporary storage, then a k j you replace it by this a maximum I k, and then the a max I k is replaced by temporary. So, that is the interchanging procedure that we follow. So, all the elements of this j to 1 to n, so all the elements in that row are, these two rows are interchanged. And then the elimination process, normal elimination process. So, again for I equal to k plus 1 to n and j equal to k plus 1 to n, we do the modifications of the elements just as in the previous algorithm. So, the elimination process, only we are adding this selection of the pivotal element and interchange of row, that is, these are the two things that we are adding in the Gauss elimination algorithm with pivoting. Now, if you solve the system, again we take example 4, again solve the system of equations like this: x 1 minus x 2 plus 2 x 3 equal to 3, 2 x 1 plus x 2 plus 4 x 3 equal to 9, and 4 x 1 plus 2 x 2 plus 3 x 3 equal to 13. So, that is what I am taking. The augmented matrix for the system is like this. Now, you can see that here 1 to 4. So, 4 is the maximum element in this column. So, I want to take 4 here and 1 here, that is what your partial pivoting we are trying to do. So, the elimination process for this system is described in the following table. So, interchanging this row we are doing first. So, we are doing here selection of pivot and interchange of rows. So, I have interchanged this row. So, first third row become first row and first row become this. Then I do the elimination in the k plus 1 to n rows. So, we are considering 4, 2, 3, 13 same, and then we are trying to, this column also we are not changing, we are changing now this one, these rows. So, this element I am making it 0 here, 5 by 2, 5 by 2, minus 3 by 2. Now, once I get this, these elements we are not changing, this I am changing to 0. Now, minus 3 by, now I have to compare these two elements, because it is 0 and this is non-zero, I will make interchange in this row. So, interchanging this row will give me again here, after interchanging the augmented matrix will look like this, and then we are getting this element here. Now, we do the elimination process and we make this element as 0, because this was already 0, I do not have to do anything, and therefore, I will get this as my final matrix, and after that back substitution process will begin. So, x 3 will be given by 5 by 2 divided by 5 by 2, that is 1, x 2 I will obtain by going to the previous step. So, minus 1 by 4 plus this, like that we will be doing, and x 1 will be obtained by the making substitutions for both the variables. Here we are substituting for x n or x 3, here we are substituting for x 3 as well as x 2, and then we get value of x 1 as 2. So, I will get x 1 as 2, x 2 as 1 and x 3 as 1 as my solution. Now, we are considering the next method, that is Gauss Jordan method, and this is another direct method for finding solution of the system of n linear equations in n unknowns, which converts the original system A x bar equal to b bar to the form I n cross n x bar equal to d bar. So, using elementary row operations, so that A if A is non singular, solution of the system is directly given by d bar, because if this becomes the system after reduction, then x bar equal to d bar is my solution, and that will be solution of the original system. So, here no back substitution process will be required. This task is achieved by extending our procedure for elimination of the element not only below diagonal elements, but also in the above diagonal elements. So, elements above the diagonal and not only restricted to below diagonal elements. That is, in the kth step of elimination process, the kth variable is eliminated from all the equations except the kth equation. That is what we are doing. So, the algorithm is now Gauss-Jordan elimination with partial pivoting we are doing again, and the input output selection of pivotal element and interchange of rows is exactly same as in the algorithm 12.2, and the details of elimination process is as follows. So, for k equal to 1 to n, selecting a pivotal element first you have to do, then you have to do interchanging of this, all these gaps are to be filled in by the previous algorithm, then we get this, then your elimination process begins. So, pivotal row element in column k plus 1 to n plus 1. So, we are considering elimination process in this. So, I will get here k plus 1 to n, again this formulas are same as the previous one, a k j divided by a k k, we are taking a k j equal to a k j divided by a k k, and then b k equal to b k by a k k. So, this is done in the pivotal row. So, pivotal element we are dividing it by the diagonal element, that is what we are doing here. So, entire row is divided by diagonal element. Then we are doing for elements in the after pivotal row. So, k plus 1 to n plus 1 columns of rows k plus 1 to n, and that is what we are doing here, same procedure as earlier, and now this additional one. So, we are doing it also for I equal to 1 to k minus 1, and the same procedure we are following. So, these formulas are applied not only to the elements below the kth row elements, but also above the kth row elements, So, we are doing it this, and then your solution will be nothing but x I equal to b I. So, Gauss-Jordan method will directly give me the solution, and if you look at the time complexity of this algorithm 12.2, the time complexity algorithm 12.2 will be essentially the same as that of algorithm 12.1, except that it will require additionally order n square comparisons and assignment operations. So, this is 12.2 and 12.3. Why we are doing partial Gauss elimination with partial pivoting and Gauss-Jordan method, both these algorithms you are considering. So, same as algorithm 12.1, except that it will require additionally order n square comparisons. Why order n square comparison? Because you have to compare every time whether a k k is 0 or not, and then you have to come maximum you have to find out, and then you have to interchange, all those things will have to be done, and assignment operations will have to consider. The time complexity of the algorithm 12.3 is almost the same as that of algorithm 12.2, as the time spent in back substitution algorithm in the algorithm 12.2 is almost the same as the time spent for processing elements in row 1 to k minus 1. Here I am doing additional processing of rows 1 to k minus 1 in algorithm 12.3, whereas in 12.2 we are doing back substitution. Both of them will almost take the same time, and therefore, the asymptotic time complexities of the algorithms 12.2 and 12.3 is not going to change from 12.1, and that will remain order n cube only, because additional efforts are order n square. Therefore, asymptotic time complexity may not be changing. Maybe that some more time will be required because of these additional operations which are to be performed, but in the when n is very large, that difference is not going to be significant. Now, example 5 we are considering, and this example 5 will be again the same as the earlier we have considered. Solve the system given in example 1. So, for example 1 we already considered this system. By Gauss-Jordan algorithm we are trying to do that. The augmented matrix of the system is this. Again we are now interchanging these rows, because this is the maximum here, and that we are explaining it here. So, this is going there and we are getting this. Then no row interchange is required, because this is already at maximum level. So, this is maximum element. So, I do not need to do any interchange here, and then I am going to make further processing of these elements. So, all these elements will change. You can see that these elements will remain same, these elements will remain same. So, this element, now you can see that here I am dividing these elements by 3. So, all these elements are divided by 3. I can see here that I am dividing all these elements by 3. So, therefore, 2 by 3 is 2 by 9, and then processing is done here, processing is done here also. So, these elements will change and these elements will change. So, we will get here, but we are not writing down all those things here, because only diagonal elements will give me the values. So, the previous values are retained here, we do not make them 0, we do not write 0, we just retain the previous values there, previous values here. So, that will give me ultimate processing 28 by 9. So, this is the pivotal element. So, I get interchanged here, and then after elimination I will get this. So, what I will get is the diagonal elements I will get, no row interchange required here after that, as it is the last row, and then I will get final like this, and whatever d bar I get will be my solution. So, solution vector is the d bar. You can see here it looks that though I am taking diagonal elements as 1, I am not making them 1 here, only to save some computational efforts. So, these are the diagonal elements 3, 3, this and this. All these diagonal elements where they are of previous step, in the current step they will all become 1 here, and all the other elements will become 0. So, if you do the manually this computations, you will get identity matrix on the right hand side and d bar on the other side. Here only we are saving the efforts to change these elements from, because of we want to reduce the computational efforts. So, what we have seen in this particular module is that we have discussed 2 direct methods. One is Gauss elimination and Gauss elimination with partial pivoting, and Gauss-Jordan elimination method for solving the systems of linear equations, n linear equations in n unknowns, whose coefficient matrix is of course non-singular. Both the methods follow the elimination process with partial pivoting. However, the first method converts the original system in row equivalent upper triangular form, in which case the solution is obtained by back substitution process, and in the second case you get the original system converted into that form, and we get directly solution of the original system. So, this is what we are talking about, the direct methods. In the next module, we will be talking about iterative methods for solving systems of linear equations. Thank you. Thank you. Thank you.